Bismillahirrahmanirrahim. ELE424 Analog Electronics 1 Diode Applications Series and Parallel. Let me change to laser pointer. Alright, okay, so Diode Application Series and Parallel. We're at Video Pack 2 Video 1. So we've completed the first Video Pack 1, which is Semiconductor Materials. We are now under the topic diode applications. Now, under this diode applications, you're gonna be introduced to a lot of diode circuits. So this is the first one, which is series and parallel. I am one Fazlida Hanim Abdullah. I'm from the Faculty of Electrical Engineering, UiTM. So the topics that we will cover in diode set 1 series parallel is, first I'm going to do some introduction so that we have an overview of the topic, as well as we go along I'll be doing some basic circuits knowledge for revision purposes, so that the lecture's description of circuits can be done smoothly and understood in a simpler manner. So we will first look at diode models and the different kind of models that we will be using, and before we go on to further diode application circuits, we'll first look at how to analyze diodes in series and parallel networks. So introduction, all of diode application contents. So we're going to have a look at all of the contents, not just for this video, not just for these slides. So from the previous PN junction topic, we know that applied bias affects diode behavior. This is the takeaway from our previous lecture. We know that there is a PN junction. Between the PN junction, that there is a depletion region, and when we apply bias, it affects how current is allowed to flow from P to N or from N to P. So in this video series, we will see how diodes behave when it is included in the series parallel circuit consisting of resistors and voltage current supply. So back to this first part, it depends on how it is biased. We know that if there is no bias, then no current is allowed to flow except for a small leakage saturation current. But if we apply, if we want current to flow, we'll have to apply forward bias, which means applying the higher potential to the P side and the lower potential to the N side. Or if we do not want current to flow, then we'll have to apply reverse bias across the PN junction, which is the lower potential applied to the P side and the higher potential applied to the N side. So now, as I was saying just now, we've studied this, we've analyzed simple circuits like this when we did circuit analysis, okay, or anything more complicated than this. But in this circuit, we usually have voltage sources and resistors, passive elements, okay. So this resistors, we know obeys Ohm's law. So if we know it obeys Ohm's law, we can do the circuit analytical techniques that we've studied, such as Kirchhoff voltage law, Kirchhoff current law, mesh analysis, nodal analysis. And when it comes to a resistor, we know that we can apply Ohm's law here, right? But if there is a diode, now that it is a diode, we'll have to decide, will the diode allow current to flow? What is the effect of the diode to the current voltages of the whole circuit? So previously, just so that we see where we're going before this, previously it was just passive elements, and maybe you have capacitors and inductors as well. But now we're going to introduce a non-linear circuit element here, which is the diode. Once we know how to analyze the circuits, okay, from this video, our next videos will be then we will use diodes to form circuits that can shape signal waveform or provide protection to a circuit. So let's have a look at a few. So we're going to cover rectifiers, and rectifiers are circuits that convert alternating to unidirectional electrical signals. So if you look at this diagram that I have here, okay, the input would be an alternating current, okay, and the output will be a unidirectional current by adding this circuit, okay, to the signal that we have. This is called a rectifier circuit. And of course, there will be other rectifiers, other structures of rectifiers that you'll be seeing. So next is clippers, and clippers are circuits that clip away a portion of an input signal. So if you put in a complete input signal sine wave, it could be a square wave, it could be a rectangular wave, it could be any wave, okay, or it could be an actual signal. So you can actually clip certain parts of the signal. You can throw away this part, okay? You can actually remove it, okay? Or you can remove just the total half, or you could remove the top and the bottom. So there'll be different circuits, but the portion of the circuit, the category of the circuit is called clippers. The next category is clampers, and clampers are circuits that shift waveforms to a different DC level. So here you have, just for variety's sake, I have shown a square wave here, and I've actually shifted the square wave from the maximum to be at V to go down to 0, and the minimum here at negative V to go down to negative 2V. So you've just actually just shifted it up and down to a different DC level. And the last category of circuits that we'll be looking at is Zener voltage regulators. So circuits to maintain a constant voltage level as a means of protection towards an intended device. So you have a Zener diode, okay? In a Zener diode here, in connection together with a silicon diode and a resistor, in which once you allow a certain condition to be met, okay, the voltage across the system that you're trying to protect will be maintained at a certain value. Okay, so this is what you call a regulator. So before we do all that, let's have a look at diode models. So this is just a list of references. So I think I've done a typo there. Bolstad is supposed to be A there. Okay, so you can have a look at this, and you should have a look at this and read it from the reference. Well, before I go off, for this particular example, maybe Bolstad have a lot of examples that may be suitable for you. Okay, diode models. So before we do analysis, let's have a look at diode models. Again, still introduction so that you understand where we're coming from. So why do we need a model for the diode? Okay, what are models in the first place? Models are mathematical relationships that describe current voltage characteristics of electrical currents. In this case, for our circuit models, if we're talking about circuit models, it's actually describing current voltage characteristics in a form of a mathematical relationship. Okay, so it has assumptions and conditions to allow us to analyze and design circuits on papers or computers. So for example, if I have a voltage source, resistor in my circuit, a load that I'm interested in to know what the voltage and the current across it should be. Now if I have a diode in the circuit, how do I handle it? If it is a resistor, I can use an Ohm's law. An Ohm's law is a mathematical model of the resistor. But for the diode, how do I deal with it? How do we describe the diode so that when I do circuit analytical techniques like Kirchhoff voltage law, Kirchhoff's current law, I know what to how to replace this diode with some mathematical expressions. And again, as I was saying just now, diode is a non-linear circuit. Now resistor is a linear circuit element because it obeys V is equals to IR. That is a linear relationship. But why do we need a diode which we know obeys Shockley's equation from our previous video? And it is a non-linear circuit. And when we do non-linear circuit, meaning that you'll be having to deal with exponential expressions of the mathematical equation. So why do we need to consider non-linear circuits when the analysis is not as straightforward as linear circuits? And the answer is because, of course, there are electronic functions that can be implemented only by non-linear circuits. And you shall see those circuits that we described earlier that we will be covering later, like rectifiers, clippers, clampers. These are circuits that can only be performed if the circuit elements in the circuit includes non-linear elements. Okay. Still, again, an introduction. Still, how do we handle a non-linear device? So diode is a two-terminal device with a non-linear IV characteristics. This is not 4, this is current voltage IV characteristics, and follows the Shockley's equation. So Shockley's equation is an exponential expression that we had earlier. Having a non-linear equation would mean having to process non-linear terms when solving the circuits, as I said just now. So we can do this graphically if we have or plot the diode IV characteristics, or we can try to solve exponential equations by hand, and both can be quite lengthy. In simulation, computers have number crunching powers, so can consider lengthy equations. What I'm saying here is that when we're doing computer simulations, we just say and find the voltage, okay? But what is actually happening is that all these equations are being processed by the computer in the background, that the computer is doing the number crunching for you, okay? But if it's on paper, Okay, even if we have all the simulations, we need to make some quick estimations when we do our design. So to make quick estimations, replacing diode models that represent the diode with the simplest elements helps simple calculations. So we will be introduced to simple models. Okay, so back to the circuit that we had. How do we deal with this equation, with the circuit analysis when there is a diode? So first, this is the Shockley's equation. Okay, it's not linear, meaning that the current relationship between ID and VD is not in a linear relationship. Instead, it is in an exponential expression. This is what I mean by doing it graphically. So usually we have this diode characteristics, and this diode characteristics is the diode behavior that is given or plotted from diode expression. So if it is a data sheet, it will give you this diode characteristics. Okay, and then this line here depends on the circuit that you're going to that the diode is connected to. So this line here is obtained from this circuit. Okay, so from Kirchhoff's voltage law, from Ohm's law, you can have this load line, and where this load line intersect the diode characteristics of the diode itself, this is just the diode behavior, and this is the circuit behavior. Where it intersects, this is what you call the operating point, and we will do a lot of this in BJT and MOSFET later as well. Okay. Alternatively, we can replace the diode with simple models. So we say, because we know that linear circuit elements are easier to handle. So what we're going to say is that we will represent as closely as possible to an ideal diode with behavior of voltage sources and resistors. So we'll have a look at several types of simple models, and this is just one of it that we might consider. Okay, diode models. First model that we're going to have a look at is the ideal model. So ideal model is when the diode is represented by an ideal diode. So what does an ideal diode do? An ideal diode that turns on just above zero forward bias, this one here, with current increasing vertically. So right just above 0 volts, it is turned on and it rises vertically. This is an ideal diode. So every time we draw the symbol, okay, we assume that it is an ideal diode. Or anytime a description of a question or a paragraph says an ideal diode, it simply means that it rises at 0 volts right after the positive of 0, just above 0. So another model that we will use is called the piecewise linear model. And here in this case, diode is represented by an ideal diode. Still, this ideal diode here is brought forward here, and the voltage source. So when there is an actual diode, it says that it is represented by an ideal diode and a voltage source. And the reason for this voltage source is to represent a diode turning on at a threshold voltage. So some books call it forward voltage, some books call it threshold voltage, and then some calls it turn on cut-in voltage. So it doesn't matter which term that you're using. It simply means that you are providing sufficient applied bias to the PN junction to turn it on, to make it forward bias to allow current to flow. So let's assume this is let's call it forward voltage here. Okay, so it will turn on at this forward voltage. So this is a bit more realistic, because all diodes that you find in this real world would have a forward voltage required for it to turn on. Okay, you don't actually find this in the ideal model, but ideal model is a simple model just to see whether it turns on and off. So if you want to include the behavior of the threshold voltage, you just add a voltage source. So silicon usually turns on at 0.7. Some data sheets might show 0.6 to 0.7, but typically it's 0.7. If it even exam questions, it does not say what it is. We assume it's 0.7, but in reality, you know that it's going to be slightly different. But 0.7 is a safe estimate. So diode is represented by an ideal diode and a voltage source and a resistor. This is another model. This is another model under the piecewise linear model. So in this model, diode is represented by an ideal diode and a voltage source and a resistor. Okay, so this is to represent not only the voltage source that is representing the diode forward voltage, but it also includes a resistor with a current voltage increase here, hence a slope after threshold voltage. So this one is going a little bit more realistic, because it's saying that after the forward voltage there is a slope and it is not vertical. Okay, so which one do you use? It depends on what is required in your analysis. Next, another model that you're going to have a look at is the exponential model, i.e. when the diode turns on, it obeys the Shockley's equation. Here you will have to handle either nonlinear equation or graphical approach. Okay, now let's have a closer look at the ideal model. So with the ideal model, if you see the diode and you decide that the diode's action in the circuit is going to be reverse biased, you replace the diode with an open circuit. So if I have a diode, okay, in a circuit, and this diode is in connection with the resistor here, with the resistor here. Okay, now if you have decided in this circuit, of course this goes on to different parts of the circuit and supplies and all that. So this part here, if you think that this diode is in open circuit, it is not allowing current to flow, if it is in reverse bias, then you replace it with an open circuit, just like, okay, then I can just replace it with an open circuit. Okay, but if I were to decide that it is forward biased, then it will become a short circuit. We'll just replace like that. That is as simple as that. Okay, this is an ideal model. But if you want to include a piecewise linear model, now we will have to replace the diode depending on what is important for the diode model. Either it is a voltage source to include the threshold voltage, the forward voltage, and the resistor, okay, when it turns on. Now this is, if you look at this slide, these terms here are slightly different. Okay, it writes here as RF for the resistance forward, because now the reason is because this comes from a different textbook. Now this is a skill that you will have to develop when you study heavy science topics, which is you're going to have different sources of knowledge, some coming in articles, some coming in journals, published reports, or it comes from textbooks, or some are very old textbooks. So different references will have different terms. So don't be afraid of this terms becoming different. Now this comes from, I think this is from the textbook Neyman. Okay, now Neyman says that if the piecewise linear model, or another textbook will call it constant voltage drop model, when it turns on, this voltage, forward voltage, okay, is represented by this value. So when it turns on, if it is reverse bias, okay, it is replaced by an open circuit. But if it is forward bias, then you replace it with this resistor. So I'm using the earlier example. So let's say this one is connected to, I don't know, resistor, a diode, okay, and to a different resistor. This goes on to another circuit, this goes on to another part of the circuit, and this goes on to another part of the circuit. Okay, if it is an open circuit, if it is a reverse bias, sorry, this will just be an open circuit. Okay, but if it is in forward bias, then this is what's going to happen. It will be replaced by a diode, a resistor, and a voltage source. Okay, we'll have a look at this example more later. Exponential model, again I'm describing the models that I've already described in the 2-3 slides ago. Again, each model at a time for each slide. So the most accurate description of the diode operation in the forward region is actually provided by the exponential model. Unfortunately, however, it is its severely non-linear nature makes this model most difficult to use. So sometimes some things are more accurate, but it's not necessarily better to use. But sometimes you need things to be accurate, then you need to find a more accurate model. So if you want it to be accurate and you want to consider the Shockley's equation, okay, analysis will need iteration or graphical approach that involves finding intersection point, or known as load line analysis. Now you can actually do this on paper as well. Okay, you can plot this on a graph paper and see where it intersects, or you can ask the computer to do the calculation for you. Alright, so this was when I meant. So in the question, if it requires exponential model, so you'll be given this diode characteristics, and from the circuit you'll need to decide the circuit behavior, the load line, and where it intersects is the operating point. Now where it intersects is what VD and ID is going to be. So which model do we use? We know that there are three: ideal, piecewise linear model, and the exponential model. So it depends on the information that you have and the information that you seek. So with limited information, use the simplest model. With simple situations, use the simplest model unless it is stated in the question. So in a computer simulation, the models have all been included in the software settings and are used in the computational process. Sometimes when you do simulations, you can say which model you want to use. Among the detailed models, that there is a choice. So okay, again, an illustration of what happens when you use different models. So let's say I want to find VD. Okay, if V1 is swept from 0 to 5 volts. Let me change this to laser pointer again. Okay, let's say I want to find VD, which is the voltage drop across this diode. And this diode has a number, IN4002. It means that this diode is an actual diode which I can buy from the manufacturer. Okay, it is in series with the resistor of 2000 ohms, and it is connected to this voltage source, which can be anything from 0 to 5 volts. Now if I use a computer, I can plot it. Okay, so let's see what happens. Now when I do the computer simulation, I just tell it to plot. I want to see what the voltage across D1 is going to be and what the current through it is going to be. So this is what the computer simulation gives me. Okay, I sweep voltage source from 0 to 5 volts. The voltage across the diode goes from 0 to somewhere around 0.61. Okay, and the current through it is, as I sweep the voltage source from 0 to 5 volts, the current goes from 0 to about 2.2 milliamp at 5 volts. Okay, so this is 2.2 milliamps for ID, and this is about 0.61 volts, which is the voltage drop across the diode. Now if I were to do hand analysis, okay, don't worry, we'll be doing our hand analysis later, but I just want to compare this before we actually do this on our own. So comparing with the piecewise model, now let's say I replace this diode, okay, with a piecewise linear model which has a forward resistance of 10 ohms and an ideal diode to show that it switches on, which, and if it is on, then this becomes a short circuit, and a forward voltage of 0.6 volts included inside the piecewise linear model. Then I can do a KVL around here, which gives me -5 plus the current across it to be 2 kilo ohm, across 2 kilo ohm to be I, and the current across the piecewise linear model to be I as well. So the current, this is a series connection, so the current will through the 2000 ohm resistor is the same current through the diode as well. Okay, so we find I to be 2.19 milliamp, and when I do Ohm's law, the voltage across the diode includes the voltage drop across the forward resistance as well as the voltage drop across the voltage source, forward voltage, and this would be around 0.622 volts. So the reason why I have included this example, this is just to compare between simulator performance and our hand calculation, is from 0.61 to 0.622, so it's acceptable. Okay, 2.2 milliamps to 2.19 milliamps. So again, it is within reasonable considerations. Now let's have a look at series connection. Okay, before we go on to do more examples, now let's have a look some basic knowledge on open and short circuits. Okay, because we're going to talk about short circuit and open circuit very often. So let's get this sorted out. An open circuit can have any voltage across its terminals, but the current is always zero. So if I have an open voltage here, an open circuit here, I will have current to be zero. Okay, but the voltage across its terminals is not zero. It can be anything. Okay, so let's have a look at a whiteboard. Okay, so now we're at the whiteboard. So an open circuit, okay, means that there is no connection. Now the voltage across this open circuit, okay, is not zero. The current is zero because this is not a complete circuit. Okay, so for example, if I have a voltage source here, so let's say this voltage source is 5 volts. Okay, if voltage source is 5 volts, current is zero. This resistor here, okay, the voltage drop, let's call this R1, let's call this R2. The voltage drop across R1 is going to be zero. Okay, because Ohm's law says V is equals to IR. So whatever the value of R is, because current is zero, voltage drop across R1 is zero. Voltage drop across R2 is also zero because the current here is also zero. But the voltage drop across the open circuit. Now, if I were to do a Kirchhoff voltage law here, okay, if I were to do a Kirchhoff's voltage law, I'm going to have -5 plus 0 plus voltage of open circuit plus 0 is going to be equal to 0. So the open circuit voltage is going to be 5 volts, which is determined by the circuit connection itself. So remember, for an open circuit, current is 0, but open circuit voltage depends on the circuit. And let's have a look at the next situation. Okay. What if I were to have a connection between these two terminals that were initially open circuit? So if I were to have this connection here, this voltage here, now let's just call it voltage 1, and let's call it voltage C. Okay, connection. Okay, now my circuit has a current that is not zero and will depend on the voltage. Okay, so VR1 will exist and VR2 will also exist. That is a non-zero value. Okay, and the voltage supply will determine what the current across the resistors are. And this voltage across connection here, because we have just connected it, okay, this means that the resistance here is 0, right? So even though the current is not 0, voltage C here, because it's just a connection, is going to be 0 volts. So basically what you've done is that you've shorted this connection, but this short here, short simply means it is connected across zero resistance. This short here does not short out any other elements. Okay, so this is just a connection. Now, what if I have a connection that shorts out another element? So this is a short circuit. So here I have, okay, this is the previous circuit. Okay, so here I still have my supply voltage, and then I have my VR1, which depends on the current here, and there is current through VR1, which is not 0. Now this is VR2. Let's see what happens when there is a short circuit connection, when we say it is shorted across R2. Okay, now current will always find the path that has the shortest resistance to flow. So if there is a resistor here that is comparable to R2, let's say there is an R3 here, okay, then I here, this I1 let's call this I2, let's call this I3. Now I1 will be distributed to I2 and I3 according to Kirchhoff current law. Okay, you see it. But in this case, I3 is a zero resistance path, so all of I1 wants to go through I3 and does not want to go through I2. Okay, so all of I1 will go to I3, and this is what we mean by the path has been shorted. So there will be no voltage VR2. It will the drop will be zero because current chooses not to pass through R2 but passes through R3. And R3 is 0 ohms. So all the current will pass through here. The voltage across this short circuit, the voltage drop across here is 0. So all of voltage drop from the power supply for the context of this circuit will be dropped across this resistor, because there are no other areas, no other resistance that would cause any other kind of voltage drops. So we're going to leave this whiteboard. I'm going to go back to the PowerPoint, and it's going to be quite a long video. I think this video is going to have a second part. So let's have a look at the silicon diode when fault biased. So we're now clear about short circuit and open circuit. Okay, so first, if you want to know, if you have a diode and you want to know how to handle it, first check what sort of model should be used. Is it an ideal diode model? Because when an ideal diode model, if it turns on, the voltage drop across it is just a pure short circuit, and the voltage across it is 0. But if the fault voltage is mentioned, such as specifically a common one would be silicon diode, it would be at typical around 0.7 volts. Then if it turns on, it will be replaced by a 0.7 volt voltage source. If it's going to be a germanium diode, the fault voltage should be 0.3 volts. Now, once you know what kind of a diode you're handling, what the fault voltage should be, next decide if the diode will turn on or not. How do we know whether it's turned on or not? Whether it's forward bias or not, and if the forward bias voltage is enough to supply the fault voltage in the direction of the diode positive current flow. So is the higher potential connected to the positive terminal? For this left diagram we have here, positive E is connected to the positive terminal of the diode. But in this right diagram here, this is a reverse bias connection. Okay, so this would turn on, but this will not turn on, because this is fault bias and this is fault, reverse bias. So is the voltage applied able to supply the fault voltage in the direction of positive current flow? So again, you know that the fault voltage is 0.7. So if E is going to be anything less than that, it's not going to be enough to turn on the silicon diode. Okay. So if yes, with let's say E is more than 0.7 volts, and it is, yes, it is forward biased. So when we draw this, we know in our minds this diode is actually behaving like a 0.7 volts voltage source, because it turns on and it locks at that value 0.7 volts. Okay, if not, then the diode is replaced with an open circuit. Okay, and if I were to do, I'm just comparing left and right here when it's forward bias and reverse bias. Okay, so if it is forward bias and it's replaced by 0.7 volts, then you do, we know VD is 0.7 volts. If we do a simple KVL, I'm going to have minus E plus 0.7 plus ID times R. But on the right diagram, because if it is an open circuit, the voltage drop across the diode is going to be depending on the circuit. But we know if it is an open circuit, the open circuit current is going to be 0 amp. So if I do a KVL here, minus E plus VD plus 0, here the voltage drop across resistor here is going to be 0 because the current is 0. So V is equals to R, I0 is going to be 0. So VD is going to be E volts. Okay, so we are now ready to go to the examples.